A new section opens here. Everything so far has described what random variables do. Information theory asks a different question. How much do you actually learn when you watch one? Take a coin. If it is fair, the flip genuinely tells you something. If it comes up heads 99 times in 100, watching it land heads tells you almost nothing at all. Same event. Wildly different information. We need a number for that. Start with a single outcome. Whatever information means, it ought to depend only on how probable that outcome was, and it ought to grow as the probability shrinks. A 1 in a million event should be more startling than a coin flip. 2 more demands. An outcome of probability 1 must carry 0 information. You already knew it. And information from independent events should add. Learning 2 unrelated facts gives you the sum of what each gives you on its own. Exactly one function satisfies all 3. The information content of an outcome x is minus the logarithm of p of x. It vanishes at probability 1. It grows without bound as the probability goes to 0. And since the log of a product is the sum of the logs, independent outcomes add up. Take the logarithm base 2, and the unit is called a bit. Now average it. The entropy of x is the expected information content. H of x equals minus the sum over x of p of x times log p of x, which is precisely e of minus log p of x. The average surprise per observation. A fair coin has 2 outcomes at 1/2 each, so h is 1 bit. That is what a bit is. The uncertainty in a single fair binary choice. Tilt the coin so heads comes up 90% of the time, and entropy falls to about 0.47 bits. Make it always heads, and entropy is 0. No uncertainty, nothing to learn. Plot it against p. Entropy is a dome. Highest at 1/2, pinned to 0 at both ends. That dome generalizes. Among all distributions on n outcomes, entropy is largest for the uniform one, where it equals log n, and the uniform distribution is the only one that achieves it. Compare 4 outcomes. Uniform gives 2 bits. A skewed distribution gives less. A point mass gives 0. Concentrating probability is the very same thing as having less uncertainty. And these numbers have a concrete reading. Shannon's source coding theorem says entropy is the average number of bits per symbol used by the best possible lossless code. Entropy is not a metaphor for information. It is the exact compression limit. The information in a single outcome is minus log p of x. Entropy is its average. H of x equals minus the sum of p log p, the mean surprise per observation, and the exact floor on lossless compression. It is maximized by the uniform distribution at log n, and it is 0 exactly when the outcome is already certain. Next, cross entropy. What happens to that average when you encode your data using the wrong distribution?